I'll also ask that everyone please keep themselves muted and hold any questions until the end unless you have a burning clarification question. Now it is my pleasure to introduce today's speaker. Yao Fu is a research scientist too at Georgia Tech. Yao received a BS in Ocean Technology from Dalian Ocean University and an MS in Climate Physics and a PhD in Physical Oceanography from the Geomar Helmholtz Center for Ocean Research at the University of Kiel. Prior to starting at Georgia Tech, Yao was a junior research scientist at the South China Sea Institute of Oceanology at the Chinese Academy of Sciences in Guangzhou. His research interests include large-scale circulation of the Atlantic Ocean, both from hydrographic observations and coupled models. His talk title today is A Stable Atlantic Meridional Overturning Circulation in a Changing North Atlantic Ocean Since the 1990s. So Yao, now I invite you to go ahead and share your screen and take it away.
Thank you, Dan. I will now share my screen. Let me know if you can see the screen correctly.
Looks good.
Good. Okay, then I will start. Hi again, my name is Yao. It's my great pleasure to be here, although not physically, but it's still very nice to be able to give a talk at the Climate and Global Dynamics Seminar. So today's talk is based on a publication that we published last year. And the title of the talk is A Stable Atlantic Meridional Overturning Circulation in a Changing North Atlantic Ocean Since the 1990s. Here are my co-authors. I have to mention that the affiliation has changed since the publication, but now let me start. Right, I believe that everybody knows what the Atlantic Meridional Overturning Circulation is. So here I will only very briefly introduce the very fundamental facts about the AMOC. We know that the overturning circulation is actually a very complicated and three-dimensional system. But however, when we name it as the meridional and overturning, we basically simplifies the three-dimensional circulation into a two-dimensional view by zonal integration. So in general, the upper ocean of the Atlantic is warm and relatively salty, and the water moves all the way from the South Atlantic, crossing the equator towards the pole. And because the water is warm in the upper layer, on the way of its northward movement, it releases heat to the atmosphere, and the density of the upper layer water becomes larger and larger. And eventually, in the subpolar North Atlantic region, the density of the water becomes large enough, and it sinks and to a greater depth, and then returns southward as a deep and cold flow. This is also relatively fresh. So in this process, a large amount of heat and fresh water transport is involved. The heat is transported northward, but fresh water is transported southward, because we effectively transport salt northward. So it's the equivalent of southward freshwater transport. And due to the role of the AMOC in transporting heat and fresh water, it has a large climate impact over a global scale. And a very classical view of viewing the Atlantic meridional overturning circulation is through the meridional distribution of water masses. And we know that the distribution of water masses in the Atlantic can be regarded as a consequence of the overturning circulation. And we also know that salinity in the Atlantic Ocean is a very good indicator for identifying water masses. And here we show a meridional section of salinity measured along this line shown in the corner map. And from this map, from this meridional salinity section, we see different water masses. And from the surface downwards, we first see a high salinity core. That water occupies the tropical and subtropical region and the main thermocline vertically. And this water mass is called the subtropical underwater, or sometimes called the maximum salinity water. This water has basically the highest salinity in the Atlantic Ocean. That is formed due to excessive evaporation between the tropical and subtropical region. And this water mass is also involved in a shallow overturning cell, which is called the subtropical cell. But of course, that's not the focus of today's talk. So below the main thermocline, we see the freshest water mass in the global ocean. That is the Antarctic intermediate water. And this water mass is formed just north of the Antarctic circumpolar current and sinks to intermediate depths and moves northward with the upper limb of the AMOC. And below that fresh water patch, we see a water mass that moves southward with slightly higher salinity. And this water mass is called the North Atlantic deep water. And this water is formed just in the subpolar North Atlantic region. And it moves southward as the deep water flowing with the returning limb of the AMOC. And at the very bottom, we see the Antarctic bottom water, and that is the densest water found in the global ocean, and it is formed along the continental slope of the Antarctic and moves northward globally at the very bottom. Because the very close link between the water mass distribution and overturning circulation, we generally would expect that the water mass property changes and overturning changes may occur at the same time. But throughout this talk, we will see whether it is the case. Now, I think climate change has become a very prominent topic. And as a physical oceanographer and climate scientist, we are, of course, very interested in knowing whether the AMOC has changed over the past or how it will change in the future. And as stated in the IPCC report, the AMOC is very likely to weaken in the coming century. And indeed, in the subpolar region, we observe quite dramatic changes of water mass properties. So here in this slide, the individual maps on the left side is the annual mean salinity in the upper 200 meters over the past few years. And if we just look at the lower panel, we see that actually a record-breaking freshening event has been observed in the subpolar region over those few years from 2014 to 2016. And a question that follows immediately is, do we also observe a dramatically changing AMOC in association with such a substantially changing water mass properties? Or let's phrase the question again, what is the state of the AMOC over the past few decades? And now with that question, we started to explore the hydrographic section data. So the reason we use hydrographic section data instead of the other data is that, first of all, we know that there are area observations, for example, rapid observation or OSNAP observation in the north. However, we know that, for example, the rapid observation only started from 2004. And the rapid the OSNAP observation is even shorter, only started from 2014. We want something a little bit longer. So with the hydrographic section data, we can go back at least to the beginning of the 1990s when we have the world ocean circulation experiment, we have many observations since then. But of course, there's limitations of using hydrographic sections because area observation are continuous observation of the circulation, but hydrographic section can only be repeated, several times throughout the years. So it's not a continuous observation. And another benefit of using hydrographic section data is that, of course, it provides us directly the information about water mass property changes over the years. And at the same time, we can use that data to estimate circulation. So as shown in this map, we've used 3 sections in this study. The first section, we name it as the Labrador section. So it consists of a world ocean circulation experiment line, AR7 West, and the recently occupied OSNEP West line. And we have also a eastern subpolar North Atlantic section that consists of the WARS AR7 East line and the recently occupied OSNEP East line. Finally, in the subtropical region, we have a subtropical section that consists of the WARS A05 line. And as you can see, all these 3 hydrographic sections are located very close to the position of the existing area observations. And in the end, I will show you that these area observations provide very important information on validating our estimates based on the hydrographic section data. All right. Let's move on a little bit. But before showing you any results about the overturning circulation, I'd like to first give you an impression about how hydrographic properties has changed over the past few decades. So here, I use the subpolar North Atlantic as an example, and I use also salinity as an example. So what I did is that because we have many repeats over the past 3 decades. And then what I simply do is I first calculate a decadal composite of salinity for the subpolar sections. And then I make a difference between the different decadal composite. So in the upper panel, it is a salinity difference between the 2000s and the 1990s. So I use the 2000s value minus the 1990s value. And in the lower panel, it is using the 2010 salinity composite minus the 1990s composite. So in other words, the 1990s here is used as a reference. And the first signal we see, of course, is very clear that in the upper ocean and in the eastern part of the Eastern Basin, which is essentially the Iceland Basin and the Iceland Basin and Rockall Trough. In the upper layer, the water mass property has changed dramatically over the past 3 decades. Compared to the 1990s, this part of the water became very salty, but actually I didn't show, but actually also becomes warmer in the 2000s. And then later in the 2010s, this part of water became fresher and also colder. And this change is very consistent with the different phases of the NAO and is also consistent with the results of Holiday et al. 2020, as I mentioned earlier. And if we now look a little bit down, deeper, when we look at the dense Labrador seawater layer, we actually see, for example, between the 2010s and the 1990s, this part of water became saltier. And actually also this part of water became less oxygenized. So there's the oxygen concentration of that water mass also decreased comparing these 2 decades. So this is the indication that the deep convection event in the 2000s is less deep reaching as it was in the 1990s. And again, when we look further deep, we have the overflow water layers. And comparing these 3 decades, so between the 1990s and 2010s, this water mass became fresher. However, in the later period, in the 2010s, this water mass became saltier. So we have a theory about the changes, but we don't know that for sure yet. We guess that this, for example, in the 2010s, this increased salinity in the overflow water is due to an excessive salt input into the subpolar basin in the previous decades, in the 2000s. But there's ongoing research to investigate the changes, property changes of overflow waters, but we don't know the answer yet. All right, so at this point, I hope that I've gave you the impression that in the subpolar North Atlantic, the water mass has changed quite substantially over the decades. And now let's move on to have a look at the overturning. Again, here's the map of the North Atlantic Ocean with the 3 hydrographic sections that I introduced earlier. So now what we do is that we take these 3 hydrographic sections, and then together with ocean boundaries, we build a enclosed box. And then we apply the so-called box inverse method to determine the absolute transport across each section, across each line in this map. So I will not go into very details about this method, but essentially what it does is that by applying the thermal wind relation and by applying conservation of volume within this enclosed box, it determines the absolute geostrophic velocity across each section. Because we know from thermal wind relation or from hydrography, we can only determine the geostrophic velocity shear, but not the absolute velocity. And this method is just designed to obtain the reference velocity, reference geostrophic velocity, and therefore to obtain the absolute geostrophic velocity. And because at each of the section, we have several repeats over the past 30 years. So we only group those measurements in the nearby years. And in total, finally, we built 8 inverse boxes throughout this 30-year period from the early 1990s to the middle of the 2010s. And here, one specific point I'd like to make is that this method allows us to utilize additional information to constrain the calculation. And here, what we use is a satellite-derived, altimetry-derived surface geostrophic velocity to constrain the calculation in order to find the reference velocity. And because altimetry data is available from 1993 and covers most of the studied period, therefore, we believe that by applying this hydrographic data, by applying this altimetry geostrophic velocity data, we are able to retrieve a very robust circulation feature. And to convince you on that point, I'd like to first show you some validation about the overturning results. But the first one is a mean velocity section in the 2 subpolar North Atlantic sections. So here the mean, what I refer to is because in the previous slide, I mentioned that we have 8 realizations. We built 8 inverse boxes throughout the years. And here in this section, the mean refers to the average of those 8 realizations. And we have the Labrador section, which is Labrador Sea, covers Labrador Sea. we have the eastern subpolar North Atlantic section covered the Erimner Sea, Iceland Basin, and Rockall Trough. Let's first look at the circulation features in the Labrador Sea. We know that in the Labrador Sea, there are two very dominant current systems. One is the southward Labrador current. The other one is the northward West Greenland current. And as you can see, these two current systems occupies almost the entire water column. And this averaged hydrography-based estimates successfully retrieved that circulation feature in the Labrador Sea. And when we go a little bit further east, we have the Erimner Basin. And in this basin, we have a very energetic western boundary current that is the southward East Greenland current. And we also see that this current system is also well reproduced by the mean hydrography-based estimates. And then further east, we have the northward Erimner current and the different branches of the North Atlantic current. And altogether, we would say that on the mean, the inverse or the hydrography-based estimates successfully captures the key circulation features. And this gives us more confidence of using this hydrography-based estimates to look at the overturning. Now, I'd like to show you another validation that is a direct comparison between the hydrography-based overturning stream function estimate with the directly observed overturning stream function. So in this slide, I first show you the subpolar comparison. On the left panel, that is the estimates from the hydrography, and on the right, it is basically the observed overturning stream function. I'd like to mention that the overturning stream function is simply calculated as a zonal and vertical integration of meridional velocity. And as you see, already noticed probably, that in the subpolar region, we calculate the overturning stream function in density space. And because in the high latitudes, specifically in the subpolar region, the isopycnals of water are inclined very strongly. And we believe that in the way of calculating the overturning in density space is will achieve a more representative overturning at high latitudes. And so on the left, the thin lines, colored lines are the individual estimates of the different years. And the black thick line is just the mean of all the individual estimates. And on the right, the thin lines is basically the monthly values from OSNAP observation. That's first in OSNAP East and lower panel is OSNAP West. And the red line is the mean of the OSNAP observation. And this black dashed line is the same as the black solid line here. It is plotted only there for comparison reasons. And overall, as you can see, the hydrography-based mean overturning structure is very consistent with the directly observed OSNAP overturning structure. And particularly for the Labrador Sea part, which is the OSNAP West, we see a two-cell structure with first a northward flowing upper layer, and then a southward flowing middle layer, which is primarily the Labrador Sea water, and then again a northward flowing overflow water layer. So that is about the comparison in the subpolar region. Now let's look at a comparison in the subtropical region. So again, on the left, it is the hydrography-based estimates, and on the right, it is just the rapid observation. And the black thick line is the mean of hydrography-based estimates, and the red thick line is the mean of the rapid observation. And overall, as you can see, above 3,000 meters, these two agree almost perfectly in the mean. But in general, we have quite successfully reproduced the observed overturning structure as well as the overturning strength. And overturning strength is simply defined as the maximum of the overturning strength function. So for example, in the rapid part, it's just this specific point where we find the maximum overturning strength function there. And also, as you all already noticed, that in the subtropical region, we calculate the overturning simply in depth space to be consistent with rapid observation. And because the isopycnal in the subtropical region is very flat, so essentially does not make a big difference if we calculate the overturning in density space or in depth space. And here are just the numbers of the mean overturning strength defined as the maximum of overturning strength function. And as you can see, they both agree quite well. So I hope at this point, I've convinced you a little bit, at least, that this inverse method works. And now let's move further to the final plots of this talk. So now we look at the overturning strength in the different years. In this plot, there are three different estimates. The first one, the red one, is calculated from the rapid observation. The thin red line is just the monthly rapid values, and the thick red line is the annual mean values calculated from rapid, and the shading is the standard error of the rapid observation. And this gray line is estimated from a simulation model, which is GECO2. Again, the thin line is the monthly value, and the thick line, gray thick line, is the annual mean value from GECO2. And the black stars with arrow bars are the estimates from the individual hydrographic estimates. And overall, we can say these three estimates agree quite well in the subtropical region. And particularly now, if we compare the different decades, the 1990s and the 2000s, the overturning strength, well, we cannot say which in which decade overturning is more stronger or less strong. So if you still remember at the beginning, I've shown you there has been quite substantial changes in the hydrographic properties. And now it seems like at least in the subtropical region, the overturning has been relatively stable. And now let's move again a little bit north to the subpolar region and look at the overturning estimates over there. So again, the colored line is from observation. That's the OSNAP observation. In the upper panel, it's OSNAP East, and lower panel, that's OSNAP West. The gray line is from GECO2, a simulation model, and the black stars are the individual hydrographic hydrography-based estimates. Because OSNAP and GECO2 did not overlap in the last few years, so we cannot directly compare the GECO2 with observation, but I just would like to point out that GECO2 is put here just for reference. As you can see now, again, when we compare, just look at the hydrography-based estimates, and when we compare the overturning values in the 1990s and 2010s, we still do not see a substantially different overturning strength. That is consistent with the results in the subtropical region. Another conclusion that we can draw from here is that the hydrography-based estimates agrees with the OSNAP observations that on on longer timescales, which is decadal timescales, the eastern subpolar basin contributes the majority of the total subpolar overturning, and the Lava Sea only contributes a fraction of the total subpolar overturning. And the mean in the eastern subpolar basin is about 16 third, while on the western side, the Lava Sea only contributes about 2/3 of overturning. And of course, you already noticed that for the GECO2, it clearly overestimates both the OSNAP observed overturning strength and the hydrography-based overturning estimates. And I believe it is not just a problem of GECO2 assimilation. It is also a problem of a lot of climate models and also other assimilation models. So in the end, we can draw a conclusion that is over the past 3 decades, the overturning was relatively stable on decadal timescales. That is the last figure, and I would like to just summarize the results as a good news and bad news. So let's start with the bad news. So the bad news is that we do observe a quite dramatically changing water mass properties over the past few decades in the subpolar region. And while the good news, or I wouldn't say it's a good news, at least it's not the bad news, is that we still don't observe a quite dramatically changing AMARC yet. That means we may still have some time, yeah. But these two together actually gives us an indication that is different from what we previously expected. So the overturning and hydrographic property changes decoupled to a much higher degree than we previously thought. Yeah, that's all. Thank you.
Terrific. Thank you so much, Yao. We now have time for questions. So I invite people to either put some questions in the chat or go ahead and raise your hand and I'll call on you individually. So I see we have one hand raised. Gokhan, go ahead.
Yeah, maybe I missed it. Did you show that the temperature changes, in other words, the density changes across the different decades?
I didn't show the temperature, but I can show you an additional plot here. So this is on the left. That's the temperature changes over the comparing between the 2000s and 1990s and the 2010s and the 1990s.
So
on the right, that's the oxygen.
Do you have the density changes, I guess, because that is going to be the determining factor, right?
That's correct, but I didn't plot the density changes, in fact.
So if the density, I mean, it looks like the temperature changes are compensating salinity. So the density changes can be really minor. In that case, hydrographic changes would be minimal, essentially.
Exactly. I agree with you.
Okay. And then you also showed differences in salinity and temperature. How significant are those differences statistically?
Right. So I don't have the plots here, but we did perform a kind of a test, a statistical test. What we did is we calculate, because we only have 8 realizations, or for temperature and salinity alone we have more than 10 realizations, but for the the overturning calculation we have 8. But I think let's say even we have 10 or 12, that's still not enough. But not enough in terms of time. So what we did is we calculate a zonal mean profile of, say, temperature and salinity. And then from that zonal mean profile, which is simply a zonal mean temperature profile as a function of depth. And then we calculated the changes of temperature and salinity relative to that zonal mean profile. And then we concluded that the changes are significant.
Okay, thank you.
Peter has a hand raised. Go ahead, Peter.
So if it isn't the overturning circulation that's caused these changes in TNS, what is it? Is it the gyre circulation?
That's a really good question. We also suspect that it could be gyre circulation. And also in this plot, Penny Holiday, in the end, they concluded that it's actually more likely the gyre circulation that brought the fresh waters from the Labrador Sea side via the North Atlantic Current and to the eastern subpolar gyre. So yeah.
And then are those changes in the gyre circulation caused by the changes in the wind due to the NAO differences?
Yes, in this paper, they concluded in that way. So it's I think they kind of inferred that it's the changes of the wind pattern that changes the gyre circulation that brought the salinity signal from the western part to the eastern part.
Yeah, because in global circulation models, when they do these experiments where they hose the North Atlantic and put a whole lot of fresh water in it, it's also true that the changes in the TNS distributions are more strongly influenced by changes in the gyre circulation than in the overturning circulation. So in that sense, I think these results are somewhat consistent with those results from models.
Yeah, thank you.
Okay, I see Ashu has a hand raised. Go ahead.
Yes, I have a question is, when you analyze this hydrographic section data, are they just repeated the hydrographic section observation? Like say, it happened on the same season for each of those observations, or it happened on different season for those observations?
Yes, that's a good question. In general, they are measured in a very similar season, not in the same month though, but in a similar season, because at least in the subpolar region, you can only that part of the ocean is only accessible in the summer. So in general, they are measured in a similar time of a year.
Okay, that means for the north side and the subtropical region, they are in a similar month.
Not necessarily. That's also a good question. So for the subpolar part, they are at least measured in a similar month. But for the subtropical region, some of the measurements are in January and some of them in May. Could be very different from the season of the subpolar regions. But here, I think I didn't mention that specifically when I introduced the inverse method. But what we did is that we applied, because when we calculate the AMOC, we need the wind, right? So from the hydrography, you can only have the geostrophic transport. We need the wind, and also we have the reference velocity calculated from the altimetry data. We always use the annual mean values for the wind as well as for the surface geostrophic velocity from altimetry. So in that way, we try to force the model to give us a results that represents the annual mean value rather than any seasonal variability, rather than influenced by any seasonal variability.
Okay. So further, like from rapid observation, we can clearly see it has very large annual cycle. Like I say, it is strongest during the winter time as much as over 30 through. But during the summertime, it can be as low as 4 through. So that means if you only use one season or 1 month data, the result can be significantly biased towards low or towards high. And although you use the annual mean wind, I'm wondering whether this effect can be fully compensated.
I believe the answer is no. So we cannot really, even though we used annual mean wind, but so the hydrographic data is still measured, say in the summer, and only represents the case, the situation in the summer. So there's definitely some limitation of this method, but we do have a error estimate from this method that is based on the error covariance matrix. And in that error estimates, we kind of compensated, or let's say considered the change due to the temporal variability of the data.
Great, thank you.
Great. I have a question. So this interesting paradigm you've set up of this sort of decoupling between hydrographic variability and circulation strength, seems to pose a question then to those results that you showed earlier of the consistent decrease in AMOC seen across models in warming scenarios. I guess I was wondering if you could talk about that a little bit. My impression from what you showed in terms of the decadal differences in temperature hydrography was that those weren't trends. Maybe you can correct me on that, but maybe it was talking kind of about internal variability that could go back and forth. And there that might show this sort of like density compensation effect between temperature and salinity that Gökhan was talking about. So I guess my question is, is there evidence here that there could, or in the hydrography, I guess in general, that there could be a similar compensating effect due to anthropogenic changes that would evince this decoupling also in the anthropogenic response? Or do you think that there are separate couplings between internal variability and the forced response?
Well, I guess this is an open question, right? So, yeah, to be honest, I'm not sure the answer exactly, but what I could say is that I believe that there is probably a trend in the hydrography observation that's not directly from this hydrographic section data, because now I analyze let's say the OSNAP array data. And that's part of my main responsibility of this job now. So we do see certain changes in the deep ocean as well. Say the overflow waters, there has been a freshening signal over the past 6 years quite consistently. So we don't know that for sure, but we do see some trend. But of course, the OSNAP data is still very short. It's only 6 years. And yeah, so that's really an open question. It could be, at this point, for now, we say there's might be a compensation between temperature and salinity and density, so that we don't see a clear change in the density structure, so there's no change in the overturning. But in the future, if say the anthropogenic change is too strong, that breaks a certain balance, and it could happen. That
Excellent, thank you. Gökhan has another question.
Yeah, if you could go back to the time series of the AMOC transport at 26 north.
Yes.
So one interesting discrepancy that this plot shows is with respect to the forced ocean models. Because regardless of the forcing, whether it's core forcing or GRA 55 or Drakkar forcing, all of the forced ocean model simulations tend to show actually an enhanced AMOC in the mid-1990s. That going up to peak value, and then it actually a gradual decline and leveling off maybe in year 2000. So it is interesting that, ignoring the deco simulations, as you can imagine why I guess are the inverse model solutions seem to be in disagreement with the forced ocean simulations?
I guess I cannot give you a concrete answer for that either. But I guess the methods are fundamentally different, right? So that's a model with a continuous varying density fields. And for us, it's basically a kind of a scattered measurements and gives only one value at a specific year. And that's why we kind of use a quite large error bars in those individual elements to kind of, taking that into account.
Right. As I actually asked you the question, I just realized that you don't have any data centered at 1995. So
That's
you,
right.
you may be actually missing that increasing AMOC event in the inverse model calculations.
That could be. That could be.
All right, well, I'm not seeing any questions. So I'd like to thank Yao again for an engaging talk and for gamely answering all of our questions. And to all of CGD, look forward to seeing you all next week. Thanks and take care.